that is merely the sum over all sequences in the typical set. But by the definition of the typical set, elements of the typical set have probabilities that are less than or equal to 2 to the minus n h of x minus epsilon. That's just by definition of the typical set. So therefore, this is less than or equal to the sum over the typical set of 2 to the minus n h of x minus epsilon. So again, it's exactly the same trick. So this, everything under this sum is constant, so we can take it out of the sum. And now this, let me actually rewrite this at the top. Equal to 2 to the minus n h of x minus epsilon, kind of the cardinality of the typical set. And where did we come from? We came from this being greater than or equal to 1 minus epsilon. So therefore, if I take this to the other side, 1 minus epsilon 2 to the n h of x minus epsilon is less than or equal to the cardinality of the typical set. So of these, that's it. That basically proves those 4 properties. So of these 4 properties, the second property is quite interesting because it tells us that property 2 says the probability of the typical set is approximately equal to 1. Or we can make it, actually it's probably better to say this, we can make it as close to 1 as we like. 3 and 4 say the cardinality of the typical set is between 1 minus epsilon 2 to the n h of x minus epsilon and 2 to the n h of x plus epsilon. But again, because we can make epsilon as small as we like, that means the cardinality of the typical set is approximately equal to 2 to the n h of x. So in other words, the typical set contains all of the probability, and it has this many sequences. So in other words, the information theoretically, the typical information theoretical strategy is only pay attention to the typical set, ignore anything outside of it, because we can make the probability of the typical set as high as possible. In other words, if there is any probability of error constraint, such as I'm willing to tolerate a probability of error of, let's say, 10 to the minus 20. In order to do that, or in order for an error to occur, you basically have to wait millions of years, even if you're transmitting at a very high rate. So if you're willing to tolerate such a ridiculously small probability of error, you can pick n large enough so that the probability of being in the typical set greater than 1 minus 10 to the 20th power. So therefore, you will basically never experience an error. And your, the cardinality of the typical set will be very, very, very close to this. So in other words, if your strategy is just to deal with the typical set, that's an excellent one because you can get as close to that as you like. Now, there's a small contradiction here, or there's a small apparent contradiction here. The apparent contradiction is that the typical set does not contain the individually most likely sequences. So, for instance, let's say we have an unfair coin where the probability, let's encode 0 as heads and 1 as tails. And let's generate sequences of flips of these coins where the probability of 0 is 0.1 and the probability of 1 is 0.9. What is the individually most likely sequence? So, what's the probability of any particular sequence? The probability of any particular sequence, these are IID events. So, the sequence maximizing this probability is what?
All tails.
All tails. That sequence is not in the typical set. The sequences in the typical set are the average sequences that contain approximately 1/10 heads and 9/10 tails. So, the individually most likely sequence is all tails. But this is not in a typical set. So for one thing, let's think of this intuitively. Although the individually most likely sequence is all tails, and even sequences that, let's say, have 95% tails are more likely than those with 90% tails. Even though that's true, such sequences are not in the typical set. But if we think of this intuitively, let's say we're flipping such a coin, and we write down our outcomes. After we've flipped the coin 1,000 times, let's say, would we expect that all we saw was all tails? Of course not. Yeah, we would expect that it would converge to the mean, and that's what the weak law of large numbers is telling us. So, although the individually most likely sequences are all tails, it turns out those individual sequences have very small probability weight. So, thought of another way, what is the probability of the most likely sequence? So let's if we take this example, the probability of the most likely sequence, the individual most likely sequence, if n is, let's say, 10,000,